All right, here we go. Today's class is on thermal radiation. This is radiation produced when something is heated. That's the thermal part. Where do we leave off? See, we've been talking this entire chapter about electromagnetic radiation. Remember, this is radiation given off by various objects, and the radiation given off has both a magnetic and electrical component to it. We talked about this thing called electromagnetic spectrum. This is, we go from longest wavelength to shortest wavelength. We could also talk about frequencies for this. Remember, frequencies is how many times per second that a wavelength cycles. Wavelength is the physical size it takes to create one individual wave. And the spectrum itself, we give names to this. The longest wavelengths are called radio waves. The shortest wavelengths are called gamma rays. Everything in between. Recall from last class that almost all things emit some form of this radiation. Remember, we're talking about the electromagnetic spectrum, that type of radiation. For instance, on the short end, you have your radio waves. That's the type of radiation. We get heat produced through infrared radiation. We get the visible light spectrum for us. That's a type of electromagnetic radiation. Our eyeballs are attuned to that. Notice that it's always on these scales shown as very large, where in fact it's actually a very small part of the entire spectrum itself. However, it's a very important part for us as humans. And then lastly, we have the higher frequency ones, the ultraviolets, the X-rays, and the gamma rays. The main point we tried to show you last class was that there's two types of reactions to this radiation. First off, something can produce the radiation itself. We call that an emitter. That's where the object itself produces this type of radiation. So for instance, if we can consider the visible light radiation, that's the visible light, there are some things that actually produce this, like a light bulb. A light bulb produces light. Now, other objects, let's say, for instance, a slice of apple pie, does not produce light, it reflects that light. However, if we expand our look to not just the visible light, but say, for instance, infrared radiation, both light bulbs and apple pies emit this type of radiation. Remember, infrared radiation is heat, and both a light bulb and an apple pie give off some form of heat. Light bulb, obviously, a bit more than the apple pie, but both of them are emitters of infrared radiation, two different bands of the electromagnetic spectrum. Infrared is lower than visible light. However, light bulbs give off both of those, whereas apple pie only gives off one. Key point here is that some things are emitters, all things are reflectors in some form or fashion. Okay, back to reflecting radiation. So visible light reflects upon this gorgeous animal right here, goes into your eyeball receives this information, your brain translates it into this picture right here. This animal itself is producing, its body itself is producing heat, which gives off infrared radiation. Here's an infrared picture of a horse. And literally, this isn't reflected heat. This is heat produced by the animal through its muscle movements that propagates through the air and eventually gets to the sensor. In this case, it's a camera. Notice in the background there is a house as well, too. House produces heat as well, too. So therefore, you can see, notice the door itself is very red. That means that that's where a lot of heat is leaking out of the house. Makes sense. The windows look like they're blue. All right, we're going to be talking briefly about atoms. So when we heat something up, the atoms start to move in a more vigorous manner. Your atoms are always in motion unless you're at absolute zero. But as you heat something up, the motion increases. And if it increases it enough, you get a very interesting effect. And that's what we're going to talk about today. You've probably noticed, and we've talked about this in the past, that when, for instance, a horseshoe is heated up, it begins to glow. Now that glow is, if our eyeballs perceive it as a glow, then therefore that object itself, that piece of steel, I think horseshoes are made of steel, that object itself is giving off light, not infrared radiation, although it is doing that as well, but it's giving off visible light. So how does an object give off visible light if all we did was energize it with a little bit of heat? Okay. So it turns out that this effect, or this this happenstance right here, happens with all objects. All objects, if you heat them up to a certain temperature, will begin to glow. A quick note, I'm going to be talking about frequency and intensity today. So frequency, remember, is the cycles per second. How many times does the wavelength repeat itself per second? Intensity is how much, for instance, we're talking about light, the brightness of the light, the intensity, and that's measured in amplitude. Now, all things, if you heat them off, give off this glow. And all things give off many of the frequencies. So, for instance, that was a light frequency. It's also, certainly since we heated it up, giving off infrared radiation. If we heat it up even further, we can also give off even ultraviolet radiation as well, too. And the interesting thing with this is that all things, as we heat them up, will give off those certain frequencies. However, the intensity, the amplitude of the wave itself will be slightly different. Some things will produce more red light, some things will produce more orange light, so forth and so on. So the question is, why does all this occur? Like, why does heating up an object actually produce light? So here's a quick 2-minute explanation of how that all works. So we start off by talking about matter. And matter consists of things made up of atoms. For instance, this candy bar is made up of a whole lot of carbon, hydrogen, and oxygen, all put together in a special form and fashion. It makes a delicious candy bar. If we focus on specifically the atom itself, as we know from science class, atoms are made up of a nucleus. The nucleus contains positive protons and no charged neutrons, packed tightly together, held together by the strong nuclear force, surrounded by a sphere of or shells of electrons that are spinning around the nucleus itself. This picture implies they're pretty close together, but in fact, they're pretty darn far apart from each other. The nucleus is closely held packet of material, and the electrons are orbiting way far away from the nucleus, but this picture is close enough. So we start off with this basic idea that electrons orbit the nucleus of all atoms. And it turns out that how they orbit that nucleus, the plus there is the positively charged nucleus, the minus there is showing you one electron orbiting a nucleus, so we have a hydrogen atom right here. And it turns out that the electron itself is in what's called a ground state. This means it's in equilibrium. That means it's perfectly happy, it wants to sit there, and no changes will occur, at least not non-chemically. Throw something else, another element next to it, and we'll have a chemical reaction potentially. If we apply some energy towards this atom in the form of either kinetic energy, movement, heat, apply some heat to it, infrared radiation, or any other type of radiation to it, we end up exciting that electron. The electron being on the outside is the first interaction it gets. And if it gets excited, in other words, it receives energy, well, it moves to a different state, and that state we call the excited state. It physically moves to a different orbit. And it will continue in that orbit. If you apply more energy, it moves to another orbit as well. It will continue this movement until the energy is withdrawn from the atom. So for instance, we're bombarding this atom with some heat. The electron moves to an excited state, moves up a level, and it will stay that until we remove the heat. Remove the heat, and it wants to get back to its original location, its ground state. Well, if it's already excited, the only way it's going to get back to its ground state is if it gives off some energy itself. And this is the glow that you see. In other words, it gives off a photon of energy, a particle of light, to get back to its ground state. And the color that that photon is depends upon how excited the atom is, or the electron is. And that's the basic idea of why when you heat something up, you give it energy, the electron becomes excited, moves to its higher orbit, and then when it starts to cool down, it gives off that energy. So the question is, if you're heating something up, it never has a chance to cool down. Well, remember, it's heating up and the outside air is trying to cool it down at the same time. So as it's trying to cool down, the amount of energy going in, it reaches an equilibrium, but it's still, part of it tries to cool down. So therefore, it's still giving off a little bit of light energy as well, too. remove the heat, then it immediately cools back down. It stops glowing. So this process itself was thought about in great detail by a guy named Max Planck. Here's an older picture of him, a younger picture, a little bit better. Max Planck was a German physicist, and he came up with this really groundbreaking idea. And he studied this thermal radiation. This was the glow produced when you heat objects up. He is credited with coming up with this thing called a Planck curve. More formally, it's known as a black body curve. Both Planck curve and black body curve mean exactly the same thing. Our book refers to it as both, but mostly refers to it as a black body curve. So we're going to talk about objects that are heated up and start to glow. All right, so we're going to start off with a quick definition of what a black body is. So Planck imagined an object, say a sphere, a basketball. And in the basketball, there's a hole. And on the inside of the basketball is a black lining. And this black lining can absorb any energy that hits it. This is an idealized body. So this is a conceptual body. There's a tiny, tiny, tiny hole in the basketball. And the basketball lets in light. So the light comes in, it starts bouncing off the inside of the basketball, and it gives up all of its energy of the light that it originally had. So all the energy now is stored inside of the black body. Once the light stops, then what happens is it re-emits that radiation back through that hole. Sometimes they make a sphere, sometimes they make this as a box. You may see both. But what's called a black body radiator, right, is this idea of light entering into an object. The object absorbs all the radiation and then it emits it back through that hole itself. We call these things black bodies. Now, it's idealized. That means it's more theoretical. Right? It's the perfect thing. We never have anything that's perfectly black that we can make. Therefore, not all the energy could ever be we couldn't create an object that actually could absorb all the radiation. So that's why we say idealized. So it's an object that absorbs all radiation, regardless of the frequency. That means all infrared, all ultraviolet, all visible. And it emits that radiation back through the hole that it came in. All right. Sounds kind of weird. This is what Planck studied. And what he got through all of his study was a pretty remarkable thing. All right, here's what he found out. If we were to measure the radiation coming out of that hole, right, and then we graph that result. Now we're going to measure it in all of its wavelengths. So we'll start off with radio waves, see what we're receiving out of that hole. We'll measure all the way up through ultraviolet. And it turns out that the shape of that curve, so on the x-axis there, we have frequencies from the longest wavelength to the shortest wavelength. And on the y-axis there, we have intensity. For lack of a better way, I'll say how bright that radiation was. So it looks like on the far left side, that's not very bright and it's a low frequency. And on the far right there on the curve, we have high frequency and also not very bright. But in the middle, you get this peak. It's kind of like a mountain. Notice the slope of the mountain slopes up gently from left to right until it gets to the peak and then drops off quickly and shortly. Okay, we call this a Planck curve. We call it a black body curve. So it's a graph of that emitted radiation, that black body radiation. All right, so where are we going with this? So we have this idealized object that sucks in all radiation and then emits it out. And if we were to measure that radiation, it would look like this. All right. Now, it is an idealized shape. The actual shape in the dotted black line there represents what a real black body curve would look like. And we're going to see a few of them today in this class. So the blue line is the general shape of the black body curve. The black line represents a specific instance of an actual black body curve. And you can see that the two are very similar, though not identical. To further confuse you, remember we can, depending upon we're measuring things by frequency or by wavelength, depends upon your x-axis. For instance, the shape there on the left, we're measuring by frequency. So low frequencies like radio waves will be on the left. High frequency like gamma rays will be on the right. And then on the graph there on the right, the colored one right there, they're measuring it by wavelength. So the short wavelength, that would be your ultraviolet and your gamma rays, are on your left, and your radio waves are on the way there on the right side of that. So we can confuse you simply by using a different graph, whether it's measured by frequency or by wavelength. But both of those, take a look at both of those, show both the idealized curve and the actual curve. Now, if you look at the one on the right there, notice it says a black body spectrum 5525K. This is the temperature of the radiation coming out. So this is the temperature of a body, not of the radiation coming out, but of the body itself. So the temperature of the black body is 5,525 Kelvin. If you don't know the Kelvin scale, it's pretty darn hot. 0 degrees Kelvin is absolute zero, and it goes up from there. Okay, so where is this going? Here's the kicker. It turns out that all objects, so Planck measured a whole bunch of objects and their black body curve, and it turned out that for a given temperature, the curves are always the same. You heat up an orange, well, I'm exaggerating, you can't really heat up an orange till it glows, but you heat up a piece of metal, it glows, measure its Planck curve, measure any other object. It can be less mass, more mass, it can be made of carbon instead of steel, and we get the same curve. You get the same curve for chocolate as you do for anything, and anything includes even human beings, or not that we're going to heat up human beings, but stars. Okay, yeah, a star is hot, but chocolate itself will give off the same black body curve as stars do. All right, and remember, you have the idealized curve there in blue and the actual curve there in black. So how can astronomy, why is this apart? Why is this important? It's because astronomers can now look at something and tell its temperature without using a thermometer, right? I can look at a star, I can measure its black body radiation, its curve, and I can tell instantly what its temperature. Why? Because Planck found out that all objects have the same curve. The one exception is the curve changes depending upon the object's temperature. This is from the book, and this shows you different temperatures. So 300 degrees Kelvin, a little bit hotter than we would like. 7,000 Kelvin, you're getting very, very, very hot. And notice that any object there that's 300 Kelvin, doesn't emit any visible light. So even though you may be giving this object energy, even though it may be glowing in the infrared, it is certainly not going to be actually glowing. We know this by, don't do this at home, obviously, but if you heat up something on a stove to where it's not glowing, you can touch it and you can burn yourself. You can continue to heat it up even further, that all of a sudden it starts glowing. Remember, it glows from left to right in this particular order right here. So it goes red, then orange, then yellow, so forth and so on. Notice that some of those peaks there peak right in the visible light. So for instance, 4,000 degrees Kelvin peaks just slightly where the red light begins. So if this object will be glowing very intensely in red, remember the y-axis there is intensity. Notice something 7,000 degrees Kelvin actually glows at a higher frequency that we can even see with our eyeballs. It peaks in the ultraviolet. So it would appear blue to us, even though because we can see blue light, but it would actually be where its highest intensity would be in the ultraviolet. Notice that all of those curves there look identical. The only difference is they're shifted left or right, or they're shifted up or down. As the temperature increases, the intensity increases. As the temperature increases, the curve shifts to the right in this case. Now, remember, if we were graphing this by wavelength, then this would just be the opposite. The intensity would remain the same. It would go up as heat was increased, but the curve would shift in the other direction. All right, we're going to take down a bunch of notes here. Since Ethan, you're copying this down, you remember you can always pause this. The shapes remain the same no matter what the object. So no matter what the object is, all objects of the same temperature have the same Planck curve, or the same black body curve. The curve shifts with intensity. More heat, higher the peak. and it shifts left to right. So the frequency changes where the peak is. The more energy, the peak moves left and right, as this second one shows right here. So all those curves have that basic shape of the curve there for the graphic there on the left. However, some have a higher intensity, more energy. The hotter they are, the higher the intensity. And notice, at least on this one, this is a frequency chart right here, the peak shifts to the right as we add more energy. All true. The curve is not symmetrical. It's not a nice little U there. If you graph it by frequency, it has a small slope going from left to right until you reach the peak, and then it has a really sharp slope going downwards. So it's not symmetrical. You're going to see this in the book. If you read the text, it talks about this thing called Stefan law. Stefan law just basically says this, that the total energy is related to the temperature. In other words, the area under each one of those curves right there. Notice 300K, it's a small mountain. So a small amount of energy. 7,000K, the mountain's about much larger. So if we calculated the area under that curve, it would be much larger. Stefan law relates to that. And it's a good one to at least know, or at least be familiar with the word Stefan's law. All it basically means, more energy is required for a higher temperature. That's kind of obvious. And the graph itself shows that as well pretty well. You've seen this, and this is a GIF. This isn't a real thing, but you heat something up, it starts to glow, and it doesn't just glow in any color. The colors change as it gets hotter and hotter. Notice the colors change. So it starts off with red, then it changes to, it's the Roy G. Biv, red, orange, yellow. If we could heat this up even further, eventually it would turn blue. We know things are turning white hot, so sometimes it's hard to see those colors. Some more notes. So no object reaches a temperature to emit anything above like ultraviolet, meaning like you can't heat something up so eventually it emits X-rays. Heat itself alone won't do that, won't make X-rays. You can't cool something down to emit radio waves, even though the electromagnetic spectrum is continuous from radio waves all the way to gamma waves. Thermal radiation can't produce radio waves or X-rays or gamma rays. Remember, what the object is made of itself has nothing to do with the curve, not how much of the stuff you have, nor what it's made of. The only thing that the curve is dependent upon is the temperature of the object itself. Okay. All this together, remember, we call it thermal radiation. It makes sense because we're talking about heating objects up. As we heat the object up, it starts to emit radiation. And that radiation, where it will emit the radiation depends upon, well, how hot it is. If it's only heated up a little bit, it will only give off infrared radiation. You heat it up a bunch, eventually it could give off ultraviolet radiation. If you've lost track of where this is all about, like why is this an astronomy class? Once again, the power of this is now that astronomers have a tool to measure the temperature of objects simply by how they visually appear. We have astronomical sensitive instruments that can read black body curves. They just have a device that can read the intensity or the scale of how much ultraviolet radiation it's receiving, how much red light it's receiving, how much blue light, how much infrared radiation, and we put that on a graph. You put that all on a graph, therefore we can predict what is the temperature of that star that we're looking for. And that's what black body radiation and curves are all about, and that's why we study them. Here's an example of one of these devices. It looks like a box. It's an expensive little box right there. We attach it to a telescope, point it at a star. We can now make a graph of the black body radiation coming off of that star. Therefore, we can now, from light years away, now tell with certainty what's the temperature of that star. And that's an important thing. We'll learn more why that's important when we study stars or suns. But astronomers always want to know, hey, how cold is Pluto? Well, point a telescope at Pluto, attach one of these devices to it, read the black body curve, and you know without going to Pluto how cold Pluto is. Here's another example of an actual black body curve. And then once again, notice there's lots of dips and peaks, but it has that basic shape. A little bit complicated here, but that's basically what it's showing. It's showing, you can read the basic curve itself. We match that curve. Notice this one's by wavelength, not by frequency. That's why notice the curve looks backwards than the previous one. Pretty complicated slide, but I just wanted to show you a real one. Our book does a pretty good job, I guess, on page 71. Now, remember, going back to this one, this is an actual black body curve. These are really idealized curves. They don't actually look like that. They look like this. But if we notice in the upper picture right there, it's showing a bit of empty space right there. Well, empty space must be cold. So notice the black body curve right there. It's reading 70 K. That's pretty darn cold. 60 K, you don't want to be out in that weather right there, but we can tell, literally in a piece of empty space that how cold it is simply by looking at the light coming off of it. Move to other objects. The second one there from the bottom there is our sun, and notice the peak there is in almost into, actually that peak there is not great for our sun, but it's close. Our peak is more into the blue for our sun. But that's a picture of a sun. I'm pretty sure that's a picture of our sun. I don't think their black body curve there is precise enough. But we receive more blue light than we see for intensity for our sun than we do others. And then the last one, you would think paradoxically that blue stars would be very cold. We think of blue as being a cold color. Actually, blue is a pretty darn hot color. Notice there the black body curve there is at 60,000 K. And the peak there is in the ultraviolet. Okay, so astronomers use this all to determine the temperature of celestial objects. Use that device, point at it, and we can now know how hot or cold something is. Inside the Hubble Space Telescope, I don't know if I've shown you a picture of the Hubble Space Telescope. There's a picture of it. Orbits about 300 miles above the Earth's surface right now. It's infamous for its mirror. Quick tangent here. When it was being constructed, it wasn't necessarily a math mistake. It was more of they were told to grind the mirror to a certain specification. They did that, and the number itself was wrong. Like I said, it wasn't necessarily someone did bad math. It was that somebody didn't really check things very well. They didn't test the whole thing. And so they launch into space, and they end up with really blurry pictures. And they had to send the space shuttle up there and a pair of basically glasses that corrected the lenses. And it was a big costly mistake, although it was triumphant, or it was a triumph for humankind, because we got some really good pictures after it was fixed. All right, another quick note, just so you know, whenever you look at this, and even in our book, notice the ones there on the left there, that's in wavelength, and I'm sorry, the one there on the right there is on wavelength, and the one on the left there is in frequency. And notice that the black body curve is just reversed. So if it measured by wavelength, the shortest wavelengths are your ultraviolets, the longest wavelengths are your radio waves. If you're measuring it by frequency, the lowest frequencies are radio waves, the highest frequencies are ultraviolet radiation. And remember, as you can tell from the graph itself, well, a couple things. One, you can see that the peaks where it drops off to zero, so it doesn't produce radio waves, it doesn't produce gamma rays or X-rays. And the second thing is it's a little bit hard to see on the one on the right there. Notice the green curve there does not look like the red curve, and yet I said they look exactly the same. And this is simply because of the fact that the 6,000 degree Kelvin black body curve, in order for it to fit on the graph, we got to squeeze it down. And as you squeeze it down, it appears that the other ones flatten out. They're not really flattened. They all look alike. Notice on the left side, it does a far better job of showing that the curve itself is basically the same curve, just the intensity changes. So if we were to zoom in on the green curve on the one on the right, it would look like the red curve, just its peak would be much lower, and because its intensity is lower.
Hot solids emit a continuous spectrum of photons called a black body spectrum. Everything in this room is actually glowing as a black body spectrum. You just can't see it at visible light, but you could see it if you switch to infrared light. This is black body radiation, but it's been shifted to the infrared where the peak is. If I want to look at this at visible light, I would have to heat the rod up. I can do that with a torch.
Struggles a little bit lighting that.
Use this torch, and I can start heating the tip of the rod. This will take a couple minutes. It will slowly get nice and hot. So the metal here should be getting warmer and warmer. We don't see anything in visible light, but in thermal infrared, it's already started lighting up. Now we'll start seeing a little cherry red glow begin on the rod. As it begins to heat to the point that now the red end of the thermal spectrum is actually getting into visible light. It'll start by glowing red. Pretty soon it will get hot enough to glow in orange. Yellow you see is just some gases and gunk blowing off the rod. And pretty soon it's glowing a really bright, cheery orange. In the thermal infrared, it's probably lighting the entire room up at this point. If I take away the source of heat, it'll start to slowly fade out. We see it going from orange to deeper and deeper red. And as it fades very rapidly as the temperature to the fourth power. Pretty soon, it's barely going to be visible at all. You can just barely see it, even in this room light. But that's in visible light. In infrared, it's probably still glowing like mad. I'll wait a little bit longer. And at this point, unless your eyes are really sharp, I can just see the red glow. It's probably barely visible on the camera. And now it's pretty much gone. If you didn't know that this was too hot to handle, you could reach out and burn yourself. But in the infrared, if you had infrared eyes, you would know right away this thing is still glowing like mad and will continue to glow like mad for some time as the energy goes away.
Okay, so the key here to remember is when we talk about thermal radiation, black body radiation, is that it gives off electromagnetic radiation in many parts of the spectrum, all the way from infrared all the way to ultraviolet. But depending upon the intensity of it, depends upon whether or not or how much of it we can see. Now notice that camera there was showing an infrared camera and a visible camera side to side. And even though we couldn't see at the start in the visible light, it was definitely glowing in the infrared. So even though it was giving off just a minute amount of visible light, it was giving off a lot of infrared light. So the intensities change. Therefore, if you were to graph that on one side where the infrared was, the curve would be very tiny, yet in the in the visible it would be tiny, but in the infrared it would be large. And that was like that 300K. So if we heated this thing up to 300K, you would see that curve. As it got hotter and hotter and hotter, the curve shifts more to the infrared, to the peak, and the intensity increases. All right, so that's going to do it for the lecture today. If you have any questions, send me an email, and I hope to see you on Monday, and I'll send you another video tomorrow.